Hello and welcome to the solutions to the first part of chapter 5. So what I've got on the screen here is problem number 4, and you probably already have the answers to this, but this is what I was looking for. So you were asked to answer the probability of A given B, and if we look at the chapter and know that the solution to that is you need to know the probability of A intersection B, and the probability of divided by the probability of B, and so that gives you 0.667. So you're given that information, and so you just need to plug in the numbers and calculate it. Same thing for probability of B given A. You should have gotten 0.80. And then C is R, and it's asking if A and B are independent, and the answer is no. And the reason why it's no is that the probability of A given B is equal to 0.667. The probability of A is equal to 0.5. If they were independent, they would be equal. That is, the probability of A given B would be equal to the probability of A, because B wouldn't have anything to do with it. And we can see that it does. For part 5, or problem number 5, you were given some information about undergraduate majors and whether they're full-time or part-time. You're asked to create a probability table. So the joint probability table is listed here. Part B, if we scroll down a little, you're given, let B equals undergraduate majors, E is engineering, O is for other, F is full-time enrollment. So we can give each of those a probability by looking at the joint probability up here. So the probability of business is this value. The probability of engineering is this value. The probability of other is this value for the other. And we see this is the highest, so business majors produce the most potential for MBA students. C says, okay, calculate the probability of E given F. Right? So F is full-time. What's the probability of engineering given that you're full-time? So we can, what's the intersection of E intersection F? So E intersection F, 1510, divided by the probability of F, full-time, which is this value here. And you get 0.2463. Going through that same process again, you have probability of F given B. We know what the formula should be. We know what the number should be up here. It's calculated out that. For E, are they independent? We calculate independence by the probability of F times the probability of B should equal to the probability of F intersection B. When we calculate all that out, we find that it's not the case, and so the events are not independent. The next item is 6, and so 6, again, you're given the joint probability table. So from the table, probability of yes is 0.42, the probability of no is 0.58. For C, probability of D given Y, again, do the calculations. Part D, D given N, probability of, do the calculations. These are the values that we're looking at. So the D intersection N is within the table, and then the N is probability of no, which are those marginal probabilities. Okay. So again, I was looking for on E something about if you drop out, you have a higher chance of, we'll just read this. Individuals who obtain college degrees have a 0.38 probability of delinquent student loans, while individuals who get a degree have this probability. If they drop out, without obtaining a college degree, they have this 58.62% probability of delinquent student loan. So by not getting a college degree, that leads to a greater probability of not paying the loans back. All right. 7 was looking for another joint probability table. So I was looking for values that look like this. Specifically then I was looking for, okay, C, PhD given female. Again, that same formula. We pull that out of our table. It should be 6.01%. Probably a male and bachelor's is this value, 0.6232. E is what's the probability the random selected applicant will be a male whose highest completed degree is a PhD. That's just this value right here, male PhD. It's that intersection. All right, number 8. Number 8, we look at the data that's given. You're asked to calculate a joint probability table. Again, here's the table that you've calculated. It should look like this. For B, it says what is the probability that the head of one of these households has a master's degree or higher. So master's degree or higher is right here, master's degree or higher. That's the 13.71% plus this probability of the doctorate. So that's how we get this total here. C is a conditional probability of 100 or more given a high school. Again, here's the numbers I was looking for in the result. Probability under 25 is 0.2. You pull that out of the table, right here. And E is a conditional probability under 25, and BD, the intersection again, and the probability of BD is this amount. So BD is right here, and 25 intersection BD, that value here. Seems to be a lot of you struggled with that. I'm not sure why. You're not following this formula. But anyhow, that's what I was looking for. For F, to show that household income is not independent of educational level. So it's not equal to, we just say probability of 100 or more given HS, and then the probability of 100 or more, so they're not equal, so they're not independent. The last problem is a Bayesian theorem problem, and all you had to do was assign what do you mean by mispayment. A customer D1 is customer defaults, D2 customer does not default. So we have probability of D1, 0.05, D2 is 0.95, probability of M given D2 is 0.2, probability of M given D1 is 1. So now what we want to calculate using Bayes' theorem, probability of D1 given that they've missed a payment. So we just plug in here's the formula with just 2 items, and we get 0.21. Since that's greater, then the question is, the bank would like to recall its credit card if the probability the customer will default is greater than 0.2. Should the bank recall its credit card if the customer misses a monthly payment? So the answer is yes, because it's greater than 0.2. Just barely, but yes. So that's what I was looking for there. And that's a review of the problems for the first part of Chapter 5.